Alright, so in the first video on 12.5 we were talking all about lines in 3-space. We did a few different things with that concept. Now we're shifting our attention over to planes. How do you come up with the equation for a plane in 3-space? Well, kind of like with lines, there's two things that you need. Two little bits of information that'll give you the equation of a plane. One, you need to have a point on the plane, kind of like how we needed a point on the line. And then you need a vector that indicates the direction of that plane. Now, this is where the vector that we use is a little bit different from what we had to do in the case of a line. In the case of a line, we needed a vector that pointed in the same direction as that line. Or you could also think of that vector as being contained in that line in a certain way. That doesn't really work for planes because if you notice, for example, this blue vector right here is in the plane, but I could draw another vector pointing this direction that would also be in the plane, and those two vectors seem to have nothing to do with each other as far as their direction is concerned. So that's really ambiguous if we do something like that. However, what resolves that issue is if we have a vector that's not contained in the plane but is orthogonal or perpendicular to the plane. That's what this red vector right here is doing. We call a vector that's orthogonal or perpendicular to a plane a normal vector for that plane, and we usually use a lowercase bold n to indicate that. So let's suppose we have some plane, this blue plane right here, and let's suppose we have that point, that fixed point somewhere in the plane, p naught with coordinates x naught, y naught, z naught again. And let's suppose that we also know some normal vector to that plane with components a, b, and c. Okay? Now, remember what we had to do in the case of coming up with the equation of a line. We had to pick an arbitrary point on that line and then relate it back to the information that we know somehow. We're going to do the same thing here. Pick an arbitrary point in the plane, let's call it P, and give it coordinates x, y, z. And then let's see what we can do with that. So one thing I notice is that we now have 2 points in this plane, P naught and P. And if I were to create a vector with an initial point of P naught and a terminal point of P, then that vector would be completely contained in the plane, right? And if that vector is completely contained in the plane, then because n is a normal vector to that plane, which means it's also a normal vector to any vector contained in the plane, I could say that this blue vector and this red vector are orthogonal to each other. Okay? So that gives me something that I can work with. But in order to do that, I need some way of representing this blue vector right here. So again, I want this blue vector to be the vector that has initial point P naught, terminal point P. And what I can do is assign position vectors to those points. So if I call r naught the position vector for P naught, r the position vector for P, then as we've seen before, r minus r naught would be that blue vector that I'm talking about. And so that whole discussion shows that r minus r naught, the difference between those two position vectors, is orthogonal to the normal vector n, which means their dot product should equal 0. Okay. Now, if I were to use the distributive property that we know holds for dot products and rearrange some things, that same equation can be written this way: n dot r equals n dot r naught. These are called the vector equation of the plane. Or either of these is called the vector equation of the plane. We rarely use that version of the equation. It's still useful, it's still important to know, but more commonly we use something called the scalar equation of the plane, and we're going to find that scalar equation basically the same way that we found the parametric equations for a line. I'm going to take this first vector equation up here, and I'm going to substitute the component forms for all three of these vectors here. N, remember, looks like A, B, C. R is x, y, z, and r naught in component form is x naught, y naught, z naught. So the difference between those would look like x minus x naught, y minus y naught, z minus z naught. And so the dot product between these two vectors should equal 0. But remember, when you take the dot product of two vectors, the result is a scalar, which is why we call this the scalar equation of the plane. That scalar equation would look like this: a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. That's your scalar equation of a plane. Okay. most of the time we are using this form of this equation, but sometimes we want to work with a simpler form. Remember, the x naught, y naught, and z naught all came from a fixed point. That makes each one of those a constant. The a, b, and c would also be constant. So if I distributed the a, b, and the c into the set of parentheses here, and then collected all of those constants, which would be negative a x naught, minus b y naught, minus c z naught, and just call that combination of constants d, then this equation can alternatively be written as ax plus by plus cd, plus cz, sorry, that should be a z, plus d equals 0. Okay, this is a little bit simpler. This equation we call a linear equation, and that might seem a little bit bizarre because when you hear the word linear, you think line, but a linear equation in 3 variables is not a line, it's a plane. This is something you explore in more depth in a linear algebra course, so we're not going to dig into that here. But either of these equations you can think of as scalar equations for the plane. Okay? Let's do an example where we're trying to come up with the equation for a plane. Now, in this case, it's not quite as simple as the first example when we found the equation of a line, because we don't have all that minimal amount of information that we need. Remember, you need to have 1 point on the plane. We have 3 this time. And you need to have a normal vector to that plane. So the key here, first of all, we've mentioned this before, any 3 points will determine a plane. Okay, so if this is P, Q, and R, one thing I can do is form the vector PQ and the vector QR, and as we saw back in 12.4, if I take the cross product of these 2 vectors, the result will be a vector that's perpendicular or orthogonal to both of them. But that would imply that that same vector is also orthogonal to the plane containing these vectors, and that's what we want. So let's start by finding these vectors, PQ. Remember, PQ is going to come from subtracting negative 3 minus 1, which is negative 4, 2 minus 6, which is negative 4, negative 5 minus 0, which is negative 5. And then do the same thing for QR. 2 minus negative 3 would be 5. And then we're going to get negative 1 minus 2, which is negative 3. And then I'm going to get 5 minus negative 5, which is 10. Okay? So the cross product of these 2 vectors, represented by these 2 arrows, is going to produce the normal vector that we want. Let's let n equal the cross product of these 2 vectors, PQ, crossed with QR, which is ijk, negative 4, negative 4, negative 5, 5, negative 3, 10. I worked this out ahead of time, so I'm just going to go ahead and give you the result. This comes out to negative 55i plus 15j plus 32k. Now can I come up with the equation of this plane? Well, yes, because this is the normal vector that I wanted. So remember, these scalars here, negative 55, 15, and 32, that's a, b, and c in that equation. X naught, y naught, z naught is any of these 3 points that I want to use. Okay, so if I let's use p, which is 1, 6, 0. The scalar equation of this plane would be negative 55 times x minus 1 plus 15 times y minus 6 plus 32 times z, I should have that where you can see the point on the screen. There you go. Z minus 0, let's just call that z, and we set that equal to 0. That would be the scalar equation for that plane. Now you might be looking at that and thinking, well, what would happen if I chose a different point? What if I chose Q or R? Then wouldn't that give me a different equation? And the answer is technically no. It would give you a different looking equation, but it would actually be equivalent to this one. And the way you can verify that is if you used a different point than I did, and if you multiplied all of the scalars into the parentheses and then combined everything into those constants so that you have something in the form of a linear equation, ax plus by plus cz plus d equals 0, then the constant that you get after combining everything would be the same as the constant that I would get doing the same thing with my equation. That's how you can verify if you have the correct answer. So this will work, but so it would also have worked if I used Q or R to get these points, or to get these values here. Alrighty. Next one. This question says, find the angle between the planes x plus 2y plus z equals 1 and 2x minus y plus z equals 4. Those are both equations for a plane. And it doesn't matter that they're not equal to 0, right? Because these are like linear equations where I just moved the constant to the other side of the equation. That's fine. This is initially a difficult problem until you kind of learn how to look at it. So here we have a picture of two planes that intersect each other, and notice their intersection is a line. We're asked to find symmetric equations for that line as a follow-up question here. But let's suppose that the angle between these two planes is theta. It's not too difficult to see that if n1 is the normal vector for the bottom plane, n2 is the normal vector for the top plane, then the angle between those two normal vectors would also be theta. See if you can convince yourself why that's the case. But it should be fairly easy to see why these two angles need to be equal to each other. So finding the angle between these two planes is the same thing as finding the angle between the normal vectors, and that's easier to do because I can find the normal vectors readily here. n1 is equal to 1, 2, 1. It's the coefficients on my x, y, and z, remember? n2 is 2, negative 1, 1. All right? And so how do you find the angle between two vectors? Well, remember we had in our section on the dot product, we talked about that. So theta will equal the inverse cosine of the dot product of these two vectors. So that's 1, 2, 1, dotted with 2, negative 1, 1, times the product of their magnitudes. Well, both of these end up having the same magnitude, root 6. Okay, this is equal to the inverse cosine of 1/6, which is approximately 80.4 degrees. All right, not too bad. You just need to know the right way of thinking about it. All right, there was a follow-up question to this, though, right? It said we wanted to find we wanted to find symmetric equations for the line of intersection. And how do you do that? How do you find symmetric equations for the line of intersection? Well, this is the line of intersection. And because it's a line, remember there's two things that we need. We need a point on that line, and we need a direction vector for that line. Now, if you think about these normal vectors for a moment, two vectors, they're contained in a plane, right? That plane is neither of these. That plane would kind of cut through both of these, but it would contain both of these vectors. And this direction vector, if you think about it for a moment, would be orthogonal to the plane containing n1 and n2. Try and visualize that. Okay? So what that means is that if I can find a vector that's orthogonal to both n1 and n2, then that vector would serve as a direction vector for my line because it would be parallel to that line. But we know how to find a vector that's orthogonal to two given vectors. We use the cross product for that. So n1 crossed with n2. In this case, remember that's going to look like I, j, k. 1, 2, 1. And 2, negative 1, 1. This works out, if you do the cross product, to 3i plus j minus 5k. Okay? Those scalars there, that's a 1 and a negative 5, those are going to be the components of my direction vector. And if we're looking for a symmetric equation, all I need is to find that direction vector and then a point on the line. Notice we also don't have a point on that line. So that becomes a little bit tricky. How do we find a point on that line? Well, one thing that we can do is kind of something similar to a previous example. Let's see if we can figure out where that line intersects one of our coordinate planes. Where does the line intersect the, let's say the YZ plane again. Yeah, I can use that one. Well, remember, the YZ plane is where x is equal to 0. So this is the same thing as saying, for what point on that line is the x coordinate 0? Well, think about where this line came from in the first place. This line is the intersection of these two planes. So any point on that line has to simultaneously belong to both planes. If I'm specifically looking for a point where x is equal to 0, I can plug 0 in for x in each of these equations, giving me 2y plus z equals 1 for the first equation, and negative y plus z equals 4 for the second equation. And if you notice now, I have a system of two equations and two variables. That's very, very easy to solve. Let's take the first equation and subtract the second one. 3y equals negative 3, which implies that y equals negative 1, which when you substitute this into either of those equations up above is going to imply that z is equal to 3. So here we have it. The point 0, negative 1, 3 lies on that line. Now we have all the information we need. A direction vector up here, a point on the line down here. Let's get our parametric equations. Oh, symmetric equations. Sorry, we were asked for symmetric equations. So using the point, x minus 0, which I'm not going to write that, over 3, that's the component of my direction vector there, equals y minus negative 1, or y plus 1, over 1. I didn't need to write that over 1, but I didn't catch myself in time, so that's fine. It doesn't matter. Equals z minus 3 over negative 5, my component for my k component up here. That's it. Got it. Those are the symmetric equations that we want. All right. We are getting close to being done with this section. It's a big section. So back in, what section was that? 12.2, I think it was. We came up with 12.1. We came up with a distance formula for the distance between 2 points in 3 space. And that's really useful. It's important to know that. But there's other ways of measuring distances in 3 space, and that formula doesn't solve all of those distance problems. So one particular problem that's useful to know how to do is to find the distance between a point and a plane. Okay, distance formula doesn't quite work there because you need 2 points, right? And even though you might be able to find a point on this plane, you don't know if it's the point on the plane that's closest to this one. You know, you need to be able to drop a perpendicular from this point, figure out what point's right there in the plane, and then use distance formula that way. And that's not a reliable way of going about it. So we have a different technique that works well. Let's suppose that you have some specific point P1 that does not lie in this plane. And let's give it coordinates x1, y1, and z1. Now let's let P0 be literally any point in the plane. So we don't have to be careful about how P0 is chosen. It does not need to lie directly below P1. It could be anywhere. And what we're going to do is form a vector P0, P1, and we're going to call it B. So that's right here. Okay. If P0 has coordinates x0, y0, z0, then we know how to find the component form of a vector, knowing its endpoints like that. So this is what that would look like. Now, what is it that we're looking for? Well, we're looking for this length right here. Now notice that line joining this point P1 and dropping perpendicular to the plane right here is parallel to this normal vector, because we want that line to be perpendicular to the plane. That's how you find the shortest distance from a point to a plane. So now if we know a normal vector for that plane, the normal vector doesn't necessarily have the same magnitude that we would want to match the length of this guy. However, if we were to take this vector B and project it onto this vector n, and specifically look at the scalar projection or the component of b along n, that would give us this length. That's what we were doing with projections a couple of sections ago, back in 12.3. Now you do need to be careful, because if you remember, the scalar component of a vector along some other vector can in fact be negative depending on which direction things are pointing. So to be a little bit more specific, we want the absolute value of that scalar projection to make sure we're getting a positive distance out of this. So again, we're looking for the scalar projection of b along n. That would represent our distance, which I'm calling d here. And we also want to be taking its absolute value. Here's the formula for that. N dot b, here's where the absolute value would show up, over the magnitude of n. Remember, that magnitude is going to be positive anyways, so we don't need an additional set of absolute value bars around that. What is n dot b? Well, again, if n has components a, b, c, and we figured out what b is all the way up here, that dot product's going to look like this big thing up here in the absolute value bars. The magnitude of n, we have a formula for that, square root of a squared plus b squared plus c squared. If you distribute the a, b, and c, and then combine the terms that have a 1 as a subscript, and then combine the terms that have a 0 as their subscript, it becomes this, okay? This is definitely a cumbersome looking formula, I will admit. But what it does is it'll tell you the distance between the point P1, which is the point where these coordinates come from, and a plane containing the point P0, which is where these coordinates come from, A, B, C being the components of its normal vector. So let's attempt to do this. I want to determine the distance between the parallel planes, x minus 3y plus z equals 1, and 2x minus 6y plus 2z equals 4. See if you can determine why these planes are parallel. Should be able, by this point, to figure that out. How do we solve this problem? Well, we just talked about how to find the distance between a point in a plane. We haven't said anything about a plane in a plane. However, if you happen to know one point in one of those planes and compute its distance to the other plane, that would be the same thing as the distance between the planes themselves. So the key here comes down to finding a point that belongs to one of those planes, and then picking some arbitrary point P0, so call that P1, in the other plane, and using this technique. Okay, so let's attempt that. I'm going to let P0, the arbitrary point, come from here. And remember, you can pick any point that you want as long as it belongs to this plane. Well, let's make it easy on ourselves. Let's find the point at which this plane intersects the z-axis. Now, the reason that's easy is because if we're intersecting the z-axis, that's where x and y are both equal to 0. I can see that if I plug a 0 in for x and y into this equation, z would have to equal 1. Okay? And you know what? Why not do the same thing over here to find a point up in this plane? Let's find where this plane intersects the z-axis. So plug a 0 in for x and a 0 in for y. What do we get when we do that? Well, I get 2z equals 4, or z equals 2. So this contains the point 0, 0, 2. Now, I'll tell you right now, it's tempting to look at this and say, oh, well, the distance between these 2 points is clearly just 1. They both live on the z-axis, and they're 1 unit away from each other. But that doesn't mean that that's the distance between the planes, right? That tells me this distance right here, not this distance. So if anything, I should be able to determine that the true distance between these planes is less than 1. Because if this distance is 1, then the true distance should be shorter than that, right? Let's see if that checks out. So we have this formula up here that we want to use. And remember, this is P1, this is P0. And then what about ABC? What is ABC supposed to be? Well, remember, ABC is just a normal vector for the plane. Specifically, it's supposed to be a normal vector for the plane containing P0. But honestly, it doesn't matter if we use a normal vector for this plane or this plane. because they're parallel, and any normal vector for this plane will also be 1 for that plane. But I'm going to go ahead and strip a normal vector out of this first equation. So normal vector in this case will be 1, -3, 1 from the coefficients on my x, y, and z right here. That acts as a, b, and c. So let's use our equation now. The distance is equal to the absolute value of a, which is 1, times times p1, which is 0. In fact, let's save ourselves some time. Notice that x1, y1, x0, y0 are all zeros. So 4 of these terms just go to 0 anyways. We can ditch them right away. C times z1, what is that? Well, c is 1, z1 is 2, so that becomes 2. C times z0, what is that? That's 1 times 1, which is 1, and we're subtracting that. 2 minus 1 in absolute value. What is the magnitude of this vector? Remember, that's what that denominator is. 1 squared plus 3 squared plus 1 squared is 11, and we take a square root of that. Finally, 2 minus 1 is already a positive number. It's just 1. And so 1 over root 11 is the distance that I'm looking for, which is definitely less than 1, like we expected it to be. Okay? I would suggest going through 12.5. If you read through the book and you look at the you look at all the examples they do, there's several examples, many of which look very much the same as the ones that we did because they're very standard examples. Mostly I kind of changed some numbers around and stuff like that. But there's a couple of examples in there that are that you have enough information now to solve, but we didn't necessarily do ones exactly like that. I would recommend scanning at the very least through the examples in 12.5 and seeing if you understand them and can reproduce them, especially the ones that look different from what we've done so far. But that should be enough to cover everything in 12.5.